Well, we've already talked about how to manage files in the operating system, but let's talk a little about the physical media that these files are stored on. And I know it seems like something we probably don't really need to know a whole lot about as a Linux administrator or for understanding Linux itself. However, there are some ways that it's useful to understand this, and you're going to see that towards the end of the presentation. So first, there are lots of different types of storage media. Your book has a nice little chart. You can see it here in the PowerPoint of various types of storage media, and I'll just talk briefly about each one of these. A hard disk is probably the oldest type that we still use today, although they're becoming less common. But basically, with a disk drive, just a traditional disk drive, you have these platters that are, you can think of almost like a record, right? For any of you that have ever seen or used a record player, you put a record on a record player, and then it has an arm with a needle that you place on the record into tracks, right? The tracks go circular around the record. A spindle and a platter in a hard drive is very similar. You can think of them like records, but instead of just one, you have maybe 7 or 8 of them. And instead of having a needle, it's a magnet that's on multiple sides, right? So you'll have a set of needles that goes in between the platters, and that's how it can read write from many platters at the same time. All the platters, when combined, they create a sector. Tracks, so you have the tracks, and then you have these sectors that are these pie-shaped things that you see in my little diagram there that came from the textbook. And basically, all of this stuff really, what it comes down to is they form blocks. So the blocks, whatever the physical architecture is, a block is how you divide that disk into equal parts. So you have all these blocks that are equal sized parts, and each one of them has an address that can be referenced. So you can tell a hard drive, go get me everything in block 5, 7, and 8, right? And it'll go out and get that for you and bring it back. And the way we measure the performance of a disk is how quickly the disk can, when you command it to either go write or read data from those blocks, how quickly can it do that? It's the seek time. The seek time is moving that armature with the read-write heads. The rotational latency, which is rotating the platters to get them in the right position. And then the actual transfer time from the write head down the wire to the interface through the SATA IDE cable or whatever it is, SCSI or whatever mechanism you're using, out to the motherboard, and then ultimately for the operating system to use it. So we tend to use hard disks to store the operating system and application software, all the stuff that we use, right? But more often than not, and you're seeing this with the lab, we're really starting to get abstracted from the concept of hard disks now, because it's all managed through our cloud infrastructure, right? And even if you're not using cloud infrastructure in Google or Azure or Amazon or something like that, there's a good chance that you're using the same technologies in a data center. So it's very rare now that we actually have physical hardware, right? It's all virtualized, and that storage is some storage platform. For example, if you go online and look up things like EMC, which is a Dell product now, or Pure and so forth, those you would use in a data center. And then, of course, they have storage technology similar to that in Amazon, Azure, Google, etc. Now, the other storage mechanisms that exist out there, one of them is magnetic tape. This is a very old technology. However, it's still pretty common, and the reason is cost, right? So basically, it's very slow tape. If any of you have ever used cassette tapes, right? If you wanted to listen to a song on a cassette tape, you'd have to rewind or fast forward, right? To go and find that track in the tapes. You'd have to move all the tape. Actually, records, which are a much older technology, were a lot easier for listening to music, because you could take the needle and place it right on the track that you want to listen to. You can't do that with a tape. You have to rewind and fast forward to get to a position in the tape. And also, if you want to make changes, that's also a little bit more difficult to do with tape, because you can only use space on that tape if the file you want to write takes up less than the space that's available from what you previously deleted. So tape, it's very difficult to use tape when you're reading and writing a lot of data. So typically tape is used for storing a bunch of data that we're really going to mostly be reading. We're not going to be manipulating that data a lot. Think about backups, for example, right? Tape is a great medium for doing backups, for saving data for long-term storage, things like that. And this is from your textbook. I don't know if it's true today, because the pricing's always going down for technology, but $50 will get you about 15 terabytes of tape, right? You can store 15 terabytes for about $50. That's pretty cheap. A hard disk, even if it's a an old-fashioned hard disk like a SATA drive that's, not solid state, it's about $100 for 2 terabytes, right? So that's significantly more expensive than that 15 terabytes on tape. So it's a great medium for storing data long term where you don't need to get regular access to it, but you need to keep it just in case for a rainy day. You also have to buy the magnetic tape drive. So the other mechanism is optical drives. So optical drives, they became popular in the 1990s when CDs came out, right? So CD was kind of the first iteration of this. There's various technologies that have come out along the way, and they were adapted for use for data storage. One problem with CDs is that it is limited in the storage, right? 25 gigabytes is about the maximum you can get on a Blu-ray, and that's about as big as they get, right? So, which is not a lot of storage for the size of the device. So they really aren't as popular as they used to be. Although I work in the medical industry, we still use them a lot for writing data for patients and things like that, but that's quickly going away as well. Think about the last time you bought a laptop, right? Most of them don't have a CD drive anymore. Most of them have no drives at all, right? For various reasons. Another medium for storage is flash memory. This is quickly becoming much more common. Your book talks about various technologies that are used for flash memory, for solid state, right? So thing about flash memory or solid state is there's very few moving parts. So less moving parts to fail, but they have failures in other ways as well, right? So they're not necessarily any more or less reliable than spinning disk, but certainly a whole lot faster because there's no moving parts. You don't have that latency from the spin and from the read heads and so forth. All of that goes away. They're great for portability because they can be very small. So they're small, they're fast. They are a bit more expensive, but for the speed that you get, it's worth it in many cases. So once we talk about the storage, it's important to talk about compression. That's in this unit in the textbook. So I wanted to talk about that before I wrapped up this presentation. There are really two types of compression we usually talk about, lossy and lossless. So lossy compression is where we lose some quality. So we're throwing away some of the data in exchange for having a smaller file size. A good example of that is a JPEG image, right? So a JPEG image, the kind that you take a picture with your cell phone, it's usually a JPEG unless it's an iOS device and they use their proprietary format. But ultimately, if you were to send it to somebody, it would be a JPEG, right? If you text it or email or something like that. And the thing about JPEGs is that most cases they're lossy images. So you lose some quality in exchange for smaller file size. And the file size reduction can be significant when compared to minimal loss in quality. Most people don't care about quality as much with these digital images because you're looking at them on smaller screens, right? So sometimes you really don't need that quality. However, it is possible, even with JPEG images, to use lossless compression. Lossless compression means it's a smaller file size, but you lose no quality. Now think about zipping files, right? So zipping is a type of compression, but you don't lose any quality when you zip something, right? How do I know that? Because I write a Word document, I zip that Word document. When I unzip it, I have the entire document. I'm not missing any words, right? So I'm getting the entire file back. And there are various mathematical mechanisms that can be used to compress these files, right? So little tricks you can use to look for patterns and things like that. And they get more sophisticated than that as you get into some more complicated algorithms. But at the end of the day, what we're really doing with lossless compression is we're reducing the file size without reducing that quality. Now, one mechanism for file compression in Linux is going to be utilities like gzip and gunzip, bzip2, zip, right? You can install all of these in your lab environment. You can use the yum command and install different utilities for zipping files. You can play with those. So zipping is certainly, common in vernacular with computing, right? Did you zip that file, or is it a zipped file, right? We use that all the time. What we're really saying is that file compressed, right? Zip used to be a trade name or a term from a certain technology, but it's come to mean just basically any file that's been compressed, but lossless, right? Zip is pretty much always a lossless compression. We're not losing any quality. And then deflate is another utility. Now, we don't always have to use compression, right? There's a simpler mechanism. So when we tar files, and you're going to see the use of tar in some of the labs, when you download files for Linux, they're usually tarred. What does that mean? It means we're taking multiple files and making one contiguous file out of them, but we're not necessarily compressing them. But there's some confusion between zipping and tarring files. In many cases, we do both. We both zip and tar a file. So we tar it first to make one contiguous file, and then we use a zip utility to then compress that tar to make it even smaller. But one of the areas of confusion with tarring is people think that it's compression, but it really isn't compression. It's really just making contiguous files. So let's say I've got a bunch of files and I store them on my disk. I talked earlier about the architecture of a hard drive, and this is the same whether it's a flash drive, tape, or you know, a traditional hard drive or CD. You have blocks, right, for storage. Those blocks are addressable spaces that are equal in size. You can see on my little fake disk I have in my PowerPoint, there are, what, 7 or 8 blocks there, right? Looks like I have 8 blocks. And each one of those blocks is exactly the same size. If I have a file that is the same size as that block, it only uses one block, right? And I can address it by that one block. However, if I have a file that's going to span more than one block, it's going to use the space in 2 blocks. The problem is when I go to store the next file, it has to go to the next block. It can't use the same space as the previous file. So in my example here, I have 3 files that are relatively small, right? So those are very small files, but they're each using just part of a block, but there's a lot of empty space there. And then, of course, you know, look at this last file I'm writing, file number 5. It's just barely too big to fit into a block, so just a little snippet of it goes into the next block, but that means everything else in that other block is now unusable. This is what storage would look like in a typical hard drive. You've got all this empty space in these different blocks. Large files will be a little more efficient, right? Because they'll span a lot of blocks, and only a little bit of the last block is going to be unusable when you have large files. But when you have a lot of very small files, then you're going to have a lot of space that's being wasted. So what can we do about that? What can we do about all that slack space? That's where the tar utility comes in. So what the tar utility does is it takes all those files and it combines them into one contiguous file. We'll call it files.tar, right? So file 1, 2, 3, 4, 5, 6, they get combined into one file, and then that one file.tar now gets stored to the disk. Now, effectively what this means, if you look at the hard drive at the top of this PowerPoint slide, we're using that entire hard drive for those files, right? There's a lot of slack space that's not being used, but there's no usable space left in that hard drive. But once I run the tar command to make one contiguous file that then gets stored on that hard drive across 6 blocks instead of, you know, the 7 or 8 blocks, now I've got 3 blocks free to write more files. So it's kind of a way that you can make more efficient use of space. What does tar stand for? It's tape archive, right? I have it written on the top of the slide. So it was originally developed for writing files out to tape. So you would make these contiguous files so you can write them to tape a little bit more efficiently. But it turns out it's still useful to use it on hard drives. It's also useful if I need one contiguous file to send to someone or to FTP somewhere, right? Sometimes it's easier to make a tar, FTP the tar file, or SFTP, I should say, or SSH, or use SCP command, or whatever command we're going to use to copy the file. We'll learn more about those later, but that's basically how it works.